into, yeah, okay. That recording in progress and notification always throws me off my game. All right, so let's dive into the actual code for this. So to first do this, the library that we're going to use in Python is the stats models library. This is just one of many libraries that include linear regression. This is just the library that we're working with today. You may encounter other libraries, but this is a good one to sort of have a baseline for. And this library works with categorical data really natively. So it is sort of your friend when you are working with both continuous and categorical. Now, one thing to note that I didn't really mention previously is that linear regression works for a dependent variable that is continuous. If you have a categorical dependent variable, you will not be doing a linear regression. You would probably do a logistic regression or some other approach. But linear regression is for a dependent output variable. So to dive into this, first we import our pandas and our stats models. This is pulling from stats models formula.api. This is just getting into the actual stats models package because stats models is a really, really big package. If you want to get more information on what's in there, you can definitely look through the documentation. Second, we are going to load in our data. To do this, we are pulling the company dataset.csv, and we're going to just pull this in. And then we're going to look at the first 5 rows of our data set. And this corresponds to what we were seeing in our case when we were conducting that first initial glance of our data. So this gives us our job titles, our age, our performance scores, education, seniority, pay yearly, and our male-female designation. Then going into our first linear regression, which was a simple linear regression, it is pretty easy. So the way that we do this is we first transform our mathematical equation into a code version of that equation. And the way this works in stats models is it is our dependent or our output variable and this little tilde, and then our input variable. And this simple linear regression is just for a one-to-one variable relationship. So this is sort of the format that it will take. Now, one way to think about this is that your input variables are being regressed onto your output variable. So you can kind of read it backwards if that helps. Otherwise, you could just remember that your output or dependent variable goes first, like it would in your equation, and then you have your input variables. So we create our formula, and here we have formula 1 equals pay yearly with the tilde age. And if we run this, we will see our actual formula there. Now, this is just a string. It's just a fancy string at this point. It's nothing crazy or extravagant. It is literally just a string that we're storing, and we're going to use it later on when we actually build our model. So this isn't doing anything yet. It's just setting the foundation for the formula that we're going to be working with. And I will rerun that just in case. So cool. So here we only use the column names. There's no need to add the name of the data frame yet, because again, we are just laying the foundation for the formula that we're going to be working with. After this, we are going to actually build our model, and we're going to use this. We're going to use the OLS function from the stats model package to build our model. OLS stands for ordinary least squares. which is the name of the process that works to minimize that sum of squared residuals, or our SSR. OLS is a very, very common approach to regression. Sometimes you may encounter other forms of this, but OLS by far is the most commonly used. And to do this, we share some code, or we develop some code to build our model. So our model 1 equals sm.ols. The reason why we have the sm dot here is because of how we loaded in that package. Then we call our OLS function, and then we pass a couple of arguments to it. The first argument that it takes is the formula, and that is our formula 1, which is what we developed, and it's this string. Now, you don't have to always have these separate. You could just put this string in here, but it's better and easier sometimes, especially if you're changing your formula a lot, to just have it as its own separate variable that you call when you're building the model. Then we have our data argument here, and that we are saying we're pulling our data frame. So this is where you're actually going to send the data frame that you're working with. Now, as you can see in this simple linear regression, we're passing this data frame with all of these variables, but we're only working with 2. That's fine. So when we build our model, what we're doing is we are laying the we're building the framework, right? So we lay the foundation for our formula, and then we build the framework of the model in which we're actually going to develop. And this is really just a computer representation of the model. It hasn't gotten any data yet, and therefore it's not going to produce any coefficients or other sort of meaningful outputs. It is literally just going to build the framework of the model. I want to see if it has what I'm thinking here. No, okay. So if we were to just call this model, it would give us information that didn't really make sense. So we could just like call this, and I can show you what that looks like. And it just gives us a description. It's like, this is a computer representation of stats models using regression, using a linear model, using OLS. That's all it is. So this is just a computer representation of our model. Cool. So in order to actually build a model that we can work with, we need to fit our data to the model. And this is where we're going to use the fit function, which is associated with our model to build a fitted model. So when we run this, we are now building a fitted model, which we can then interact with as our linear regression. So now our model has been fed data, but it is still only an object that is stored within our computer. So if we call fitted1, it's just going to give us another weird code thing that says stats model, regression, linear model. But here we see that it's the regression results wrapper. So we do have results and we have fitted our model, but by just calling it directly, it's giving us this computer representation of it. We need to get into the actual model to get to pull out the different information that's in it. So here, even if we print it, it's still going to say the exact same thing, and it's not really going to give us the details. We have a question here. What does it mean to fit a model? This means that we are building the best model based on our data. And it's a computer way of just putting data into our model and creating the model in the background of the computer way. We're fitting the model to our data. In a machine learning sense, you may run a model a number of times to find the best fitting model. Here with the linear regression, you just have to do it once. Okay, so fit is not doing anything with, fit is not determining that it's a linear regression or anything like that. This OLS is where we're saying it's going to be a linear regression. Because OLS is one approach to linear regression. It's an ordinary least squares approach to linear regression. So once we have the fitted model, we can use the dot summary function to pull out the regression results. And this is what I mean by using a function to access information inside of the fitted model that we can then understand. So if we pull that out, we get the regression table that we have seen in the entirety of our analytical case. And so this should look pretty familiar. Now, one thing that I also want to highlight is that this these regression results include skew and kurtosis. Skew and kurtosis may sound familiar, but skew is basically whether or not our data is shifted left to right. And kurtosis is what is the extent to whether our data is super tall or super short. So this gives us some indication of the shape of our data. For these other things, if you want to, you can look into them. Like Durbin-Watson, Jarque-Berra, like these are statistical tests. Omnibus is another statistical thing. It's just ways to talk about or to understand the shape of the data that's being fed into it. Cool. Okay, so the way that you build a regression is first you define your formula. Here we did that with our formula one, pay yearly regressed onto, or age years regressed onto pay yearly with the little tilde. Then we pass our formula to OLS. This is where we're saying, we're going to do a linear regression. We're going to do it with the OLS method. Here's the formula that I want, and here's the data that I want. Then we're going to fit it to actually build a working model and get sort of information using our data. And then we print summary to output the results from our fitted model. So we could put all of this into one cell and run it all together and immediately get our output. And this output should be the exact same as the one that we see up here. But they don't have to be like in separate code cells. You can just run them in one flow. Cool. So this is a simple linear regression. If we wanted to, well, we'll do that in a second. But with this fitted one model, with our fitted model, say we wanted to pull out other information and not just the summary, we could use other functions to get that information. So, well, other sort of elements. So we can get our parameters or our params, which gives us the coefficients for the different variables that we fed into our model. So if we run that, we get our intercept and our age here. We could also get the p-values from our fitted model. And here we get intercept and age, just the p-values. And this data will match up with what we see here. Now, a fun thing is that we see with p-values, it's actually giving you the full value. It's not rounding it like it is in the table. So we can see just how tiny these actual values are. So this is to the negative 29th power. So that is, or 10 to the negative 29th power. So that is moving this decimal point 29 places this way. So it's going to be 0.00000 all the way up 29 places until it's 500. So this shows you how how tiny those p-values really are. And then we can also get the r-squared value, which is up here, by pulling this r-squared. And again, this is going to give you a non-rounded version, so it's going to be more accurate. So here we have 0.23777739, whereas in our table, we only get 0.238. So it's really useful to get these different elements. Now, there are a number of these that relate to all of these things that you can see in the summary. They just have different names. And you can get a full list of attributes by running this directory fitted one, which gives you all of the attributes of our fitted model. I'll actually just run that so you can see it. And you can see all of the different things that exist. So there's a lot of different things that go into stats models, and this is really where it's powerful. A lot of this stuff relates to sort of more advanced statistics, but you can get a lot of information about your model. And now that we have that, I'm just gonna delete that. Okay. So now if we wanted to run a multiple linear regression, it is really just as simple as adding those additional columns into your formula. So if we wanted to include age plus our gender, we literally specify our age years column plus our male and female column. And it sort of represents this equation, which we saw previously in the analytical case. So when we run this, we will build a new formula. And we can just keep adding plus signs to add more things into this equation. Sort of like just as if we were doing with an actual mathematical equation, it's just simplified here because the code is expecting it. So we can just add plus sign, plus sign, plus sign, and keep adding in new variables if we wanted. So now we're going to use this formula and we're going to create a second fitted model. The rest of the code is exactly the same as our simple linear regression. We're just using a different formula. So here we get the output of that. This again corresponds to what we were seeing in our analytical case. So we get our details. Again, we're mainly looking at our r-squared value, and we're mainly looking at our coefficients and the p-values. Awesome. All right. Oh, I just blew past that question. So what is the r-squared of this model? Try to access it using only the fitted model's attributes. So try and access it using what we went over up here with these. Cool. So yeah, so again, y'all are catching on pretty quickly. It is just as simple as calling the fitted to and getting the dot r-squared, which is a component of our fitted model. See? Okay, so now we're going to try and build this model using age, our male and female category, and our education categorical variable. Feel free to share your formula in the live chat. Looking good indeed. Cool. So yeah, so y'all are getting the hang of it. It's literally just adding in that education column using a plus sign. And then the rest of the data is the same, or the rest of the code is the same. We just update it for our formula 3, and then we get our regression results. And this is the exact same table that we saw in our analytical case. So we don't have to go over it too in depth. Again, it's using college as our default education. It's using female as our default here. So yeah. Cool. So adding categorical variables, as you can see, is just very simple to the model. You just have to include them as you would any other variable. Now, this is the case with stats models. Other packages may have other quirks. If you see something like, and this actually is a benefit of stats models, but if you see something like this, with a C in front of it, that is just explicitly stating that it's a categorical variable. Stats models will work with that, but you may see that in other cases. It does not change anything in stats models. So here, even if you look, we've got 0.29 as our R squared. If we take that out and run it again, we still get 0.29. So it doesn't change anything for this package, but you may come across that if you're using other packages. And it's just an explicit way to state that that variable is categorical. I want to go over that because it's not necessarily included in this case, but you may see that in practice. Cool. Okay. So so here we're regressing job title onto pay yearly. We're running through our code, sending over our formula, our data, running our fit, and then printing our fitted model, or the summary of our fitted model. And this is where we see the different job things. I think the associate executive or whatever it's called is missing. So that's our default. And we have the other jobs titles represented here. Cool. All right, so there's some questions. Is there any difference with categorical variables like dummies? You can, my question is, why would you do all that work when the model can do it for you? If you do need to actually explicitly state it, you would just add them, like the best practice is to just add the dummy coding as additional columns into your original data set, and then use the dummy coded variable in your formula rather than the original variable. Cool. The tilde, which is this little curly bit, in this case means is regressed onto, but you read the formula backwards. So it's like job title is regressed onto your output or dependent variable. Okay, cool. All right, so let's code this model where we have our yearly pay, our intercept, the age, our male female category, our education category, and our job title category. Um, Somebody asked about explicitly defining a categorical variable. Don't stress about that because stats models understands that this is a categorical variable, but sometimes you might see a capital C with the variable in parentheses. And that is an explicit way to state that a variable is categorical. And that comes up in other packages, but for stats models, you don't need it. It just understands the assignment. Okay, cool. So the solution that we have here is our formula 5. We have our pay, our age, plus male, plus education, plus job title. So these are our input variables being regressed onto our output variable. And then we have our model that we're building. Again, when we call this, we're just saying, hey, computer, build the framework for a linear regression model. So it's not doing anything yet, it's just building the framework. Then this model fit here, it's taking what we gave it and say, actually create the model. And then here we're showing the parameters of our values. So these are just the coefficients. Cool. So the intercept here is that the base salary with all variables at 0 is 59,523. Okay, so there is a question about how do you test assumptions for a linear regression. You do that in other code. So like creating a scatter plot to show relationships between variables, creating a histogram to show the shape of the data, creating a coefficient matrix to see, or a correlation matrix to see the strength of relationships between variables, and looking at basically the scale or the distribution of data. If it's massively like different scales between one variable to another. So like say one variable goes 0, 10, 100, 1000. That's a logarithmic scale, whereas another variable is like 1, 2, 3, 4. Those do not have the same homogeneity of variance. They have different variance. They're heterogeneity. They have heterogeneity of variance. So you would need to modify one, usually doing a log transformation on one data, to have them have homogeneity of variance. Okay. I don't know what you mean by deterministic in this sense. This version of a linear regression is used for inferential statistics. So it is used to make predictions using the line that's developed and the regression that's developed, but also to understand the variables that are being fed into it. This is not like a pure machine learning approach. All right. I think I answered the question of how does OLS determine which function to use as baseline. So yeah, so it can go alphabetically. Some models on the back end will take the first one that it encounters in the data and go with that as the baseline. But honestly, you interpret it as you're reading. So in this case, it's probably doing it alphabetically. Yeah, for stats models, it's going alphabetical. Cool. Yes, it is very simple to build linear regression in Python. It's all the data cleaning and testing assumptions that are the hard part when it comes to linear regressions and building a good model. because that's a lot of conceptual work. How do you know what the default variable is in the categories? You would just know what the categories are in that variable, and the one that's missing is the default. That's an easy way to do it. Okay. When you add columns to a linear regression, you are giving the linear regression more data. So the more data it has, the better it's going to be able to model the real world, unless you give it really bad data. So it's just creating a bigger and bigger model. So it explains more of the variation in your output variable. This is probably one of the easier ways to do linear regression. Linear regression, though, is easy across packages. To answer Carlos's question, but there are different ways to do it. So, but this one is probably one of the easiest. And the benefit of this approach is that it feeds into more machine learning mechanics of this idea of defining the model and then fitting a model. That fits more into later machine learning approaches. Does it have any category limits? I don't think so. Is there a simple way to create dummy variables? In pandas, there is a function called create dummies. That's probably the easiest way to do it. Wow, y'all ask really tough questions. Y'all are like putting me on the game. But that's the end of this case, really. It's just, and you can play around with this. I think one of the best things to do is to find a data set with some continuous variables and just play around with it. Start exploring the variables, looking at sort of the elements that are in that data set, the shape of the data, and then build out a couple of linear regressions. Play with it. A dummy variable is just a categorical variable that's broken out where each element is a 0 or a 1. A p and an alpha. Okay, so the p value is, let me actually start over. The alpha is a value that we determine going into our hypothesis test, essentially, or statistical test, where we set a limit and we say if it's under or below that, if it's under this, then we know that it's going, that what we're seeing exists in so few cases that our values are important, right? And that's where the p-value comes in. It's how statistically significant our values actually are. So if the p-value is less than the level that we set, we can say that we can make conclusions about our hypothesis. If the p-value is above our alpha, then that means it doesn't meet the threshold that we set and we can't go with our hypothesis. But depending on specificity, you may set your your alpha to like 0.01 or 0.001. In which case it is a much lower threshold that you have to, or it's a much higher threshold that you have to pass, but it's actually a much lower value than your p-value has to be. If you 0.05 is basically saying that like 95% of your data and 5% of your data. If it's 0.01, it's 99. and 1%. If it's 0.1, it's 90% and 10%. And if you look at this sort of range up here, this range corresponds with that alpha level. So if we set 0.05, well, actually this is set at 0.0, never mind, I take that back. But this is basically the range of that we're setting in association with our alpha and our p-values. Okay, lots of hard questions that you guys are passing at me. I'm trying to answer them the best I can. The 0.05 is not related to your R squared. The R squared is how well your model is explaining the variation in your data. So a p-value and an alpha are different than your R squared. A p-value and an alpha are for hypothesis testing. The R squared is the overall best fit of the model for the data that it's being modeled on. Yeah, and if you see like an R squared of 1 or like 0.99 or something like that, that's kind of scary. You probably want to go back to your model and check that something's not going weird with your data. And that's even more so when you're doing like a logistic regression. If you're getting like that level, that means that your data is entirely like something's flawed. Okay, so I think that's everything. I'm going to pass it over to Monica and DS4A, which I think is Oscar. But if people have questions or anything, they can always reach out. And I'll try my best to answer them. Some of the questions that you guys answer, though, are really like at the level of like statistics PhD. And like the best advice that I would say is like, don't stress, because no data scientist is like working at that level unless you are like building brand new models at like Apple or Google. And even then you're dealing with a team of like 20 people who all have PhDs in math. So it's a different ballgame. All right.
Thank you so much, Jonathan. And that's true, guys. You're not going to be alone in a team, like never, never. And you also know how to do that because you're working in teams right now. So Jonathan, it has been like a terrific pleasure to have you here tonight. And I know our fellows are a little bit tired, but we hope you all like this lesson and learned a lot. So just go and rest, and we're going to see you tomorrow. Thank you again, Jonathan. Have a great night.
Thank you.
Bye, guys. Take care. See you tomorrow.